Parrish at QCware. Tonight, I am very excited to be telling you about a brand new capability that we have just introduced into our Promethium quantum chemistry solutions product. That capability is the Analytical DFT Hessian, implemented for the first time on graphical processing units. I know that's quite a mouthful, but it's actually a very important capability that we believe is going to be quite useful in designing molecules and materials using our Promethium solution. So before we go into a demonstration of the capability, a very natural question is why do we need this object? The answer is it is ubiquitous throughout quantum chemistry. The Hessian is that quantity which we use many different ways to connect the very rough conception of a molecule and the property you care about for that molecule to an actual for real computation of that property. For just one example here, under the heading of thermodynamics, we very often use the Hessian to explore the potential energy landscape and calculate things like free energy differences. As we go from a reactant to a product over a barrier involving a transition state, all of those energies are actually free energies, not just electronic energies. And the nuclear enthalpic and entropic contributions to those free energies is typically computed using the Hessian under what's known as the harmonic formalism. There are many other cases when exploring chemical reaction networks that you also use the Hessian. And another example would be the particular mode, the imaginary frequency over the barrier here, we use to calculate the reaction rate, actually, and to actually try to predict what that reaction rate would be in a real-world system for that. That's just one area. Another area that is very common, a little bit more work person-like, is structure optimization. That is, after you've done the work of optimizing the structure of a molecule to find either a minimum, which you hope looks like a reactant or product, or a transition state, which is obviously transitioning between the two of those, you will very often look at the Hessian and look at the eigenmodes, one of which is depicted here for a transition state, and determine from the eigenvalues and eigenvectors there whether you have actually found a minimum or a transition state or something else. And so it's a very good validity check of a lot of the calculations that we do using the energy and gradient in other parts of quantum chemistry codes. Yet another area where it is extremely important is in spectroscopy. In fact, in this case, often the Hessian is the observable that you are asking about, the property you're looking for. For instance, if you're looking at Paxlovid, this molecule right here, and you want to know its IR spectrum, there it is. And it's basically just the eigenvalues of the Hessian. And so the answer is lying directly inside the Hessian in that particular case. So these are three major areas, and there's probably another half dozen we could talk about. But just take it from me, the Hessian is woven throughout quantum chemistry, and we use it throughout to predict a number of direct observables and to do a lot of validity checking and speed accelerations of the code if you have a nice analytical Hessian available for that. So it's obviously very important. What is it? Well, it's a matrix, and I'll show you sort of how it emerges in one slide here. By now, you all are very familiar with uploading the coordinates of a molecule, and for that XYZ point of the molecular potential energy landscape, you calculate, by solving electronic structure in Promethium or other codes, a single scalar, which is the energy, right? So that's given by a single number block here for this particular molecular geometry here. And you know that if you move those X, Y, and Z coordinates of these atoms, you get a different energy. And there's a bunch of different energies as you go through all possible motions of that molecular geometry. But really, that's the feed-forward process, is you just take X, Y, Z in, and you get an energy from that. By now, you're also quite familiar with another thing, which is often called the gradient. You may know it as the force vector on the atoms. And it's given by a slightly larger counting block thing here. In fact, a vector of counting blocks instead of a single scalar here. And what this object is it's the answer to the question, what happens to the energy as I take each atom and I move it in X or in Y or in Z? How does that energy change with respect to motions in this direction of moving that atom there? And so you make a table of all of those different, this atom X, this atom Y, and so forth, and you end up with this vector quantity of derivatives, first derivatives, called the gradient. And a very weird thing about electronic structure theory is that actually by the time you've calculated the energy and solved the Schrodinger equation to do that, you pretty much have all the information you need to calculate the gradient. And so you'll often see that the gradient and the energy for a given method take about the same time as each other. You see where this is going. There's a third open space here on the plot here. And yeah, that's going to the second vector, or two vectors is a matrix in math land. And so that's exactly where it's going. What we're going to do now is we're going to ask for each gradient perturbation. So I go to this atom and I move it in X. I ask, what's the gradient of that gradient entry? And so for each gradient perturbation on the row, I take a full gradient on the columns. Now a second derivative, moving this atom and maybe this atom over here. And that gives me this matrix with many, many different entries in it, which tell me how basically, if I move this atom in X and this atom in Y, what's the simultaneous second derivative of that energy as I do that. This is obviously a much larger object. And unlike the first two, it doesn't cost the same amount as the first two. It costs one order higher in the number of atoms in the system, and that's simply a topological fact. But that having been said, we can still write a very efficient code that can actually analytically evaluate that Hessian much more quickly than a conventional finite difference approach would be. Because what you may do in many cases, and we used to do this, is literally take every atom and perturb it backwards and forwards in X, finite difference, and take a gradient at each one of those displaced geometries and staple them all together, and you get one row of the Hessian. You do that over and over again, and you end up with a complete Hessian. That's called a numerical Hessian, and it's inaccurate. Usually its accuracy is actually okay, but there may be some questions about accuracy. It's also very slow. And so when you code an analytical Hessian, it's a lot more work on the code side of things, but the resultant is much, much faster. And so that's what we have done, is actually go ahead and implement that for what we believe is the first time on graphical processing units, at least the first time with this kind of speed that goes with it. And so this is an example of the kind of thing you're going to see when you go run Promethium and encounter the Hessian now, is for a system like Paxilvid, which has on the order of 60 plus atoms, running a pretty conventional hybrid DFT, B3LibD3, and a Def2 basis. No problem with basis set or anything like that. You could run trip zeta or whatever you wanted for this, I think up to H functions. And you want to run an analytical Hessian for this. That's going to cost you about 2 minutes for the full Hessian of this thing, which is already quite a large matrix that you're calculating there. And this should be contrasted with even the Promethium really fast gradient code being used in a finite difference procedure. It takes 2,000 seconds, so more than a half hour, closer to 3/4 of an hour with that. And we are 13.1 times faster than ourselves with numerical, and so our finite difference. And so the analytical code is over 10x faster, actually 13 in this case times faster, than doing even a pretty optimal numerical approach. And down in the 2 to 3 minute regime, which is actually quite tractable to use routinely when you're doing geometry optimizations or transition state searches or things like that. And so a very, very nice speed up that we're seeing across the board, and you're removing any of the inaccuracies that may have come with the finite difference when you did the numerical finite difference Hessian for that. So let me go ahead and switch windows and actually show you this in action. I believe the window I'm looking for is this one, which actually has, I'm logged into Promethium here. I'm going to show you just one of many places. It's already, so the analytical Hessian is pretty much plug and chug it in what you've already done throughout Promethium. So we're going to run a workflow you may have already run verbatim. You just didn't get an analytical Hessian. You got a numerical finite difference Hessian the last time you did this. We're going to go ahead and optimize the geometry of, I'm just going to call it Paxilvid demo. And we'll use an A100 GPU. And we're going to go ahead and upload. I just happen to have Paxilvid lying around here. It's a neutral singlet. And this is it. It's a pretty rough geometry for it, actually. It's an okay looking molecule, but it's not actually all that close to an optimized structure for that. And we're going to go ahead and first we're going to optimize it, because this card is the geometry optimization workflow. So we're going to try to find the minimum structure, or a minimum structure. If you want to make sure you found the minimum structure, you should use conformer search. But we're going to try to find a minimum structure of this molecule. And one last thing we're going to do, and this is going to activate the analytical Hessian, is we're going to compute the vibrational frequencies of that optimized structure at the very bottom of the calculation. And in particular, we're hoping that if we have optimized the structure well, all of the vibrational frequencies are real and positive, meaning that you're going uphill as you go away from the optimized molecular geometry. If you find that you don't get that, you're actually at a saddle point, a higher order thing like a transition state, and you have not found a minimum on the potential energy surface and need to do some more work. So this isn't just one example of using the Hessian to validate and get some more confidence in the results of something like a geometry optimization. We're going to go ahead and run it and submit it, and it will go ahead and run for you. I'm afraid I have already talked for so long that it's probably better for me to just actually walk you through one of these that just finished. This overall calculation on a 60 atom plus system, and not an easy optimization, takes about 15 minutes using the analytical Hessian. It takes well over an hour with the, in fact, quite a bit over an hour with the numerical Hessian. And here's what we're going to do is first I want to show you the geometry optimization. So what we did is we started from that previous structure, and this is the molecule optimizing and just relaxing, and you can see it form an internal hydrogen bond here, which is really nice like you'd expect. And it's actually, this group is kinking out a little ways, and it's basically just relaxing a little bit and finding an optimal structure as, fairly close downhill from that initial guess structure that you gave it. But another thing that happens is we now have these vibrational frequencies. These are the eigenvalues of the Hessian matrix. And one of the very key things that we need, as we were just talking about, is these need to all be positive and real if you are at a minimum. And they are. Some of them are, in 20 wave numbers regime, which is fairly small, but they're all positive, and that means that this is a local minimum on the potential energy surface, and we can have a high degree of confidence that we haven't accidentally stumbled upon a transition state or other saddle point kind of geometry with that. And so just one of many, many places throughout Promethium where this analytical Hessian will be activated if you happen to run into a case where you were already using a numerical Hessian. Let me just give you an example of, this is the log file from the optimization. And at the very bottom of it, beyond just printing, the vibrational frequencies, which that row is the most important, positive, this card is just showing you that we've actually fallen into the analytical Hessian computation, and it ends up only taking 15 minutes overall instead of over an hour for this computation because of that capability that we have for that. Actually, at the moment, the Hessian is so fast that much of the time is spent in a geometry optimization, which is a good problem to have. And so with that, I will conclude and wish you all well. And by the way, the Hessian is now implemented for hybrid density functionals. Everywhere that you can use the core density fitting algorithm, the Hessian will run nicely out of the box, with the exception that we have not yet implemented the Hessian for PCM solvent, for LRC, less long-range corrected hybrids like omega PBE, and or for meta functionals like MO52X. All of those last three are just work person-like items that we have to get to in the code development, but not as hard as the initial implementation of hybrid density functional Hessians on the GPU, which was a brand new undertaking for the purposes of this release that we're talking about here. But if you have any need for those three capabilities, PCM, LRC, or Meta, please let us know. It's on the roadmap, and we should be able to get to it fairly soon. But if you have any particular need for it, let us know, and we'll try to move as quickly as possible on that. Otherwise, enjoy using your new analytical GPU-powered Hessian in Promethium. Cheers.